Let's say video or audio. Does it say video or audio?
Audio.
Let's see. All right. So welcome everyone to finals week at the University of Washington, and we're starting out strong with the defense of Michael Rosenberg. I'm excited to see so many familiar names and faces today. I guess it's one of the small benefits of doing this via Zoom. Michael joined us here in 2015 after he got his bachelor's in mechanical engineering at North Carolina State University. Along the way, he also has gotten his master's, and of course today he is here to defend his PhD to hopefully become Dr. Rosenberg. Before we got started, I just wanted to share a little bit about his path here at UW. He's received a number of prestigious fellowships, including the College of Engineering Fellowship his first year here at UW, which let him rotate through a few labs, and we were really excited for him to join our group. He also was a recipient of the NSF Graduate Research Fellowship. This last year has been quite the interesting one for Michael, to say the least. He arrived in Minnesota last spring, and I think was there for about 2 weeks, with our 1 or 2 weeks with our clinical partners at Gillette Children's Specialty Healthcare, before unfortunately getting sent home due to the pandemic. But he's done a really nice job pivoting in the past year. And although it meant that he wasn't able to get as much clinical and experimental time, that he was really able to dive deeper into some of the exoskeleton and computational methods that he'll be sharing with you today. And so today he's going to be telling you all about his exoskeleton research, or what we often call ankle-foot orthoses. And often we see this as a very glamorous area of research, right? Everyone loves their exoskeletons. And so we often have this as the vision, but I like to remind people that this is hard and dirty work. And so the reality is that it often takes a lot of hard work in the lab to collect and process this data. Now, I also, just before we began, wanted to share a couple of the other special things that Michael has done during his time at UW. One of them in particular is, I think that Michael has really become known as a mentor extraordinaire in our lab, or we call it the undergrad wrangler. He's become really a leader in helping to mentor undergraduate students. And I even see a few of them on today. So I'm really glad that you guys were able to join. And he's been able to not only shepherd multiple of them into helping get the NSF Graduate Research Fellowship and positions at other universities, and of course have taught them all the valuable skills at conferences, from not only presenting posters, but all those other vital skills that we need to do at conferences. Let's see. Also, he's become the editor-in-chief of a journal, which I am sure I've heard is now up to 10 publications. And also, as appropriate and stereotypical for any University of Washington PhD student, he is also quite the mountain master and has helped many students summit multiple peaks here in the Seattle area. But I really liked one of these quotes from one of these folks who was dragged / encouraged up a mountain, that I'm sure anyone else who has hiked with him will agree that he wields a limitless source of energy, and something that we should potentially study in the future. And I have no doubts that he'll continue setting this pace in his postdoc and beyond. So we're really excited to see the steps beyond, but we're also really excited today for him to share some of his research and what he's been working on so hard these last few years. So while we wish that we would all be in person like this, today we are continuing like this, and this is what our lab has looked like for the past year. But we really are excited that you all could join us for today. And with that, I'm going to turn it back over to Michael Rosenberg for his defense. All right, Michael, it is all yours.
Thank you. Had I known so many pictures would have been taken of me, I would have been more careful. Okay. Can everybody see that all right? Excellent, excellent. Thank you, Ken. I appreciate the kind words and mentorship and guidance that you've provided to me over the years. And I also want to, of course, thank my committee, Drs. Steele, Hafner, Burden, Proctor, and Shen, for the support they've given me, and I look forward to their very challenging questions at the end of this. So throughout my PhD, I've really sought to uncover why ankle exoskeletons impact gait and mobility in so many different ways for so many individuals. And so I'm excited to talk a little bit about what I've discovered and developed in the process. But first, to give everybody a little bit of historical context, exoskeletons are absolutely nothing new. This is a device from, I believe, 1889 to assist walking and running. And back around 1900, there was this big surge in development and patents related to ankle exoskeletons, or exoskeletons in general. But only in the last 2 decades has there been a resurgence of interest in exoskeleton design. And that recent uptake actually coincides with a real explosion in research into these lightweight, often energetically efficient devices called ankle exoskeletons. And you can see an example here of a passive ankle exoskeleton that in this case was used to reduce the energetic cost of walking. So these are really exciting devices and they have a lot of potential to assist gait. They come in a variety of designs. In a clinical context, they're generally called ankle foot orthoses or AFOs. And they're prescribed to individuals with motor impairments, such as those with cerebral palsy or individuals post-stroke, to assist locomotion and improve kinematics. Generally, those are a solid piece of thermoplastic or composite whose mechanical properties can be modulated to resist ankle flexion as a way to modulate gait. State-of-the-art ankle exoskeletons can be passive, like the one I just showed you, or powered, such as this wearable robotic exoskeleton developed by Zach Lerner's group at Northern Arizona University to reduce the energetic demand of walking in children with CP, or cerebral palsy. Now, if you're like me and you aren't making state-of-the-art ankle exoskeletons, you might fabricate something bulkier, a little bit more covered in duct tape, like this device that I used in my dissertation research to perturb locomotion and help us model responses to ankle exoskeletons. But regardless of design, all of these devices have similar mechanical interactions with the user. And the most commonly studied interaction is the torque generated at the ankle to assist or resist ankle flexion. It can be generated in different ways. For example, in a passive ankle exoskeleton with an extension spring in parallel with a shank, stretching that spring generates a force that pulls at some moment arm relative to the ankle, and that generates a torque. For a powered exoskeleton, the torque profiles can be an arbitrary function of a control policy as well as the actuator dynamics and limitations. But regardless of design, really what we're trying to do when we study exoskeletons is figure out how to customize them, to tune them to an individual to elicit desired improvements in mobility. And this isn't the same for everybody. In fact, exoskeletons have fairly complex impacts on gait. From center of mass mechanics to joint mechanics such as joint angles and moments to muscle activity, exoskeletons can alter these different features of locomotion that can be relevant to achieving successful walking, achieving efficient walking, and moving stably. Now, these aren't the only impacts of ankle exoskeletons, but there are a few that I'll focus on in my dissertation. To give everybody a little bit of intuition as to what an exoskeleton can do, let's take a look at one young man with cerebral palsy walking in the gait lab at Gillette Children's Specialty Healthcare. Now, you can watch him walking barefoot here, and you see number one, he walks fairly slowly, and number two, his left knee never fully extends. So now let's see what happens when he walks with bilateral passive ankle exoskeletons. We notice number one, that he walks a little bit faster. And when he comes back in the other direction, you'll see that his knee extends a little bit more during stance. So those would generally be considered positive outcomes, but this is just one case. And if we look across individuals with cerebral palsy, for example, we see a very different story. This is a figure from a study in over 300 children with diplegic cerebral palsy, walking with and without ankle exoskeletons. So they computed the change in this case, the gait deviation index between walking with an exoskeleton and without. And the gait deviation index is a summary metric of kinematics, where an improvement is generally considered a good thing and a degradation in GDI is generally considered a bad thing. And what you can see is that some kids get much better, some kids get much worse, and there's a small average change. But I really find the tails of that distribution interesting. It makes me wonder, why do some people change in one direction? Why do some people change in the other? And we and other researchers have found that it's really hard to predict these responses. Even in unimpaired adults, we observe heterogeneous responses to ankle exoskeletons. This is some of our data. We had people walk in a zero stiffness exoskeleton and a high stiffness passive exoskeleton. And we found that changes in muscle activity, in this case, the gastrocnemius biarticular plantar flexor calf muscle, some people increased activity over the gait cycle, some people decreased, and the average change was small. But this shouldn't be terribly surprising, because if even in unimpaired adults, differences in physiology like muscle strength can influence exoskeleton responses. And those differences are amplified in individuals with motor impairments due to the uniqueness of brain injuries as well as motor experience over the lifespan. So our question of customizing exoskeletons really becomes one of being able to consistently elicit changes in gait across individuals with diverse physiology and motor experience. So how do we do that? Well, the way I like to think about it is that being able to enhance mobility comes down to being able to encode individual physiology in our exoskeleton design process. And I think there are two big ways to do that. One is improving our ability to predict responses across individuals. And the other is quantifying mechanisms that drive these heterogeneous responses. And I don't talk so good. Those two goals are really the focus of my dissertation research. And I work to develop methods and make discoveries to advance both of those objectives. The broad premise of what I'm going to talk about is that subject-specific dynamical data-driven models can improve our ability to predict exoskeleton responses and can guide investigation into mechanisms driving those responses. Now, to be clear, when I say subject-specific dynamical data-driven models, that's a very broad class of model. They range from physiological models, which give us insight into the impacts of ankle exoskeletons on things that can be hard to measure, like muscle force or joint loads. On the other end of the spectrum, we can look at purely data-driven models that help us encode exoskeleton responses without requiring specific measurements or knowledge about an individual's physiology that we need to construct physiological models of locomotion. And in between, we can consider physics-based models that help us understand how exoskeletons impact task-level control, essentially high-level control of locomotion. And my dissertation uses each of these frameworks to try to understand gait with exoskeletons and responses to exoskeleton properties. Specifically, this is all working towards being able to model and predict responses across a broad range of individuals. So we did this by first using physiological models to predict responses to ankle exoskeleton designs, different designs in children with cerebral palsy or CP. We then evaluated the ability of purely data-driven models to encode responses to ankle exoskeletons without knowledge of an individual's physiology. And finally, my latest work, which I'll spend some time talking about, used physics-based models to quantify changes in how individuals control task-level variables when walking with ankle exoskeletons. Now, I discussed the first two subsections here in my general exam, but I'll go over them briefly and then dive into my third aim in more detail. This first aim has been published in the journal PLOS One. And what we really wanted to know was how ankle exoskeleton design can impact muscle demand in children with cerebral palsy. A big motivation there is that the energetic cost of walking is elevated in CP compared to typically developing children. And a particularly costly gait pattern is crouch gait, which you see here, and it's characterized by excessive knee flexion and ankle dorsiflexion. To address this question, we took data from 12 children, 3 typically developing and 9 with cerebral palsy and varying levels of crouch severity. And we simulated walking unassisted, as well as with 3 different types of bilateral ankle exoskeletons. We used the musculoskeletal modeling program OpenSim to do this, and we evaluated 2 powered exoskeletons, one that assisted plantar flexion and dorsiflexion as much as needed, one that assisted only plantar flexion, which is similar to contemporary powered exoskeletons. And we tested an optimized passive exoskeleton, where we optimized the device stiffness and neutral angle to, again, minimize, in this case, the sum of muscle activation squared, which was the objective function of all of these simulations. We quantified the overall impact of the exoskeleton using what we call leg impulse. So that's just the sum of muscle impulses across all muscles in the lower limb. And we found that all 3 exoskeleton designs, which you can see up here, reduced leg impulse across our crouch severity groups. We also found that powered exoskeletons generally reduced muscle demand more than an optimized passive device, but the change was not always large, for example, in individuals with severe crouch. We then dug in to try to understand where these reductions in muscle demand occurred. And we found that they almost entirely occurred in the ankle plantar flexors, the soleus and the gastrocnemius. What you're looking at here is the percent change in muscle impulse for these individual muscles, and the colors denote the crouch severity groups. We see that, in this case, the powered ankle exoskeleton essentially took over work for the soleus, a uniarticular plantar flexor, and had variable impacts on the gastrocnemius, a biarticular plantar flexor. So we dug into that a little bit, and we found that the peak knee flexor moment, during stance for all 3 exoskeleton designs was negatively associated with percent reductions in gastric impulse. That means that an individual who exerted a greater knee flexor moment tended to see a lower reduction in gastric impulse. So in summary, the main contribution of this work was that it was among the first to predict exoskeleton responses using musculoskeletal simulation, and to my knowledge, the first in cerebral palsy. We found that while powered exoskeletons can reduce muscle demand more than passive devices, that additional reduction may not be worth the added complexity of a powered device. We also found that children who walk with lower speeds may benefit more from exoskeletons, and that joint mechanics may predict muscle level benefits of exoskeletons. And that concludes my first aim. And while these physiological models that we used provided insight into the exoskeleton impacts on muscle demand, they required specific measurements and a lot of assumptions about the individual. And so the second thrust of my PhD really focused on improving our ability to predict when we may not have a specific set of measurements, or when we can't validate our assumptions about a specific individual. This work was in collaboration with Drs. Sam Burden and Bora Vanyanen, and it's published in the Journal of the Royal Society Interface. I discussed this in more detail in my general exam, but briefly, just to recap, we tested 3 models of varying levels of complexity, starting with a phase varying model, which predicted our kinematics purely as a function of phase, or it predicted outputs purely as a function of phase in the gait cycle. It was agnostic to exoskeleton torque, and we expected it to have low prediction accuracy. Our linear phase varying model was linear with respect to our measurements and exoskeleton torque, and varied nonlinearly in phase and with our prediction window delta. A nonlinear phase varying model was our most complex, It was a feed-forward neural network that was nonlinear with respect to all of our variables, and we expected it to provide an upper limit on prediction accuracy if we had enough data and the right data. So we specifically hypothesized that this linear phase-varying model, due to the small perturbations from a passive exoskeleton, would predict with greater accuracy than our phase-varying model and would predict as accurately as the nonlinear phase-varying model. We tested this by collecting data in 12 unimpaired adults walking on a treadmill at steady state wearing bilateral passive ankle exoskeletons. We modulated exoskeleton torque by changing out extension springs that were attached in parallel with the shank. You can see that here. And you can see the resulting torque profiles from one participant. We then modeled response to the exoskeletons as the deviation from an unforced gait cycle, being the zero stiffness condition. So that's what we were trying to predict, specifically that change relative to the K0 average gait cycle. We measured muscle activity and recorded motion capture, so our inputs to each model were kinematics and muscle activity. You can see just an example here, kinematics on top. You see that the largest impacts are at the ankle, which is what we expect, with smaller and more variable impacts in muscle activity. What we found, and I'm going to show an example specifically for ankle dorsiflexion, but this generalizes across our kinematic outcomes. We found that both linear and nonlinear models predicted kinematic responses pretty well. To test this, we used 3 conditions where we held out one of our 3 non-zero stiffnesses, which have been noted by these different dashed lines. And then we fit our models, and then we predicted on the held out condition. So you can see an example of our experimental and our predicted responses at the ankle. So qualitatively, we did pretty well. We quantified this using relative remaining variance, which you can think of as 1 minus r squared, where 0 is a perfect prediction, and you can predict a value of 1 by predicting the average of the data. There's a lot on here. The colors denote the models, and the shapes denote our holdout conditions. We found that across all 3 of our holdout conditions, that the LPV model predicted with significantly better accuracy, greater accuracy than the phase varying model. And we did not identify differences between the linear and nonlinear phase varying models, which supports our hypothesis and suggests that linear phase varying dynamics are an appropriate way to encode unimpaired responses to passive exoskeletons. However, we struggled to predict myoelectric responses to ankle exoskeletons. Here are just 2 examples in the gastrocnemius and tibialis anterior. Again, the black denotes our data, the orange denotes the linear phase varying model. And while we did a decent job predicting the average responses across these 3 holdout conditions, we really failed to capture the stride-to-stride variability in the dynamics. And so that suggested to us that we might be missing something in our measurement set that could help us predict these exoskeleton responses. In summary, this work established phase-varying models as a tool to predict kinematic responses to ankle exoskeletons without requiring any knowledge of an individual's physiology. We showed that linear phase-varying models could encode these responses, but that we might need new measurements to encode myoelectric responses to ankle exoskeletons. And in particular, this challenge of predicting myoelectric responses got me thinking more about our ability to quantify and understand the mechanisms that underlie diverse responses to ankle exoskeletons. And it's really hard to identify those mechanisms due to the heterogeneity in physiology and in control. So that prompted me to return to a more fundamental level and ask why. Why do we observe changes, certain changes in response to exoskeletons? And can we provide a foundation for that future investigation? I did this by investigating changes in task level control. And I'll talk a little bit more about what I mean in a couple slides. This work is in collaboration with Dr. Josh Proctor, and we have a manuscript in preparation. The reason to connect our measurements to task level variables, I'm going to talk about center of mass motion. And I'm going to do that because controlling the center of mass is fundamental to walking, to getting between 2 points, doing so efficiently and doing so stably. Center of mass motion is often quantified using low-dimensional models, often called templates. These models attempt to encode task-level control using mechanical elements, such as rigid limbs, curved feet, or leg springs. And each of these elements encodes a hypothesis about how an individual accelerates the center of mass. Moreover, these models really form the foundation for the physiologically detailed models that I described in my first aim. There are two particularly interesting aspects of template models of center of mass motion. The first is model structure. Which mechanisms do we include in the model? And each mechanism describes a characteristic pattern of acceleration. The parameters of those mechanisms describe the magnitude and direction of impacts on center of mass acceleration. And both of these factors can be useful in differentiating between different individuals or different limbs. Let me talk about a couple examples of why looking at center of mass motion with exoskeletons can be so interesting. The first is that ankle exoskeletons alter center of mass mechanics and energetics. In particular, center of mass power, the power that each limb generates to accelerate and decelerate the center of mass, is altered by passive empowered ankle exoskeletons. Additionally, following neurological injury, the people who most frequently use these devices, limb contributions to center of mass acceleration and power can be altered. For example, post-stroke, individuals tend to generate more negative power and less positive power with their paretic limb. Now, these studies are incredibly insightful, but what they don't tell us is why. Is this simply a change in the energetic profile of the system, or does it correspond to a change in task level control of walking? So that's what I really wanted to understand with ankle exoskeletons. And I thought that parameterizing the center of mass dynamics using this template-based framework could highlight characteristic responses to ankle exoskeletons and really provide a foundation for us to investigate more biologically realistic mechanisms. To do this, we sought to answer 4 questions. The first was, how do we do it? And I'll talk a little bit more about why that's not a trivial question in just a few slides. We then asked if center of mass control strategies were consistent across unimpaired adults, or if there were individual specific strategies that may help us differentiate between certain types of responders. Then we got into the really interesting aspect, which is how does center of mass control change with ankle exoskeletons? And finally, to gain a little bit of insight into what might happen following neurological injury, we performed a case study in one individual with hemiplegic cerebral, with post-stroke hemiparesis, and investigated changes in center of mass control with ankle exoskeletons. So let's get into this first point. The reason I say that it's non-trivial to select a method to identify these template-based signatures of locomotion is that a great many mechanisms have been used to describe walking. And each of those mechanisms describes a characteristic pattern. So it's possible that those descriptions may differ between individuals. Additionally, particularly in individuals with motor impairments, the signatures or these mechanical representations may be asymmetric. For example, that was something proposed in studies of children with hemiplegic cerebral palsy. So how do we do this? Well, Fortunately, there's an algorithm that's essentially designed to do exactly that. And it's called hybrid Cindy. I'm going to walk you through at a high level how we used it to build template representations of locomotion. Cindy, for those of you who aren't familiar with it, stands for sparse identification of nonlinear dynamics. And it's an algorithm that identifies parsimonious representations of system dynamics from a library of candidate dynamics terms, or mechanisms in our case. So that provides a model identification step, where we take observed motion and we describe that in terms of these candidate mechanisms, such as rigid limbs, spring legs, or rotary forcing mechanisms. Hybrid Cindy extends Cindy in two important ways. The first is that it uses clustering. It applies Cindy over clusters of similar measurements to identify dynamics within hybrid regimes of the gait cycle. For us, we might consider those regimes single and double limb support defined by the foot contact configuration. And we may expect different dynamics in each regime. The second important extension is using information criteria to trim away unnecessary mechanisms in a model selection step, to select a model that's both parsimonious and highly representative of our system dynamics. In this case, we use the Akiike information criterion, which does exactly that. It balances model complexity and prediction accuracy to give a generally sparse, highly predictive model. And the end product of this, we're going to call a characteristic template signature for each individual. So this is a subject-specific modeling pipeline. So our first question is, does it work? Hybrid Cindy has been applied for hopping and to model disease progression. So it's really promising, but it hasn't been extended to walking. So the first thing we did was generated a synthetic data set of walking in a spring-loaded inverted pendulum, or SLIP. Now, this SLIP model contained leg springs and dampers, and it was a 3D representation of locomotion. For the time being, you can ignore these terms up here. So we generated about 4 minutes worth of gait cycles, similar to what we had in our experimental data. And we populated a mechanism library for the Cindy algorithm. We included the leg spring and damping terms, the slip mechanisms, and we also included rotary stiffness and damping, these terms that you see here, which weren't included in the simulations, but we put in the mechanism library to ensure that hybrid Cindy could correctly omit missing or dynamics that didn't impact center of mass motion. So we apply this algorithm. We fit the dynamics to the accelerations of the center of mass. The Q denotes generalized coordinates. And we found that it performed quite well. What you're looking at here are the model mechanisms on the bottom and their coefficients on the y-axis, the single and double limb support. The gray bars denote the ground truth, what we want to achieve, and the clear colored bars denote the estimated dynamics. And we found that, especially in single limb support, even with noise, our model predictions were quite good. We could accurately reconstruct the dynamics. In double limb support, we did a little bit worse, but that was expected based on our choice of hyperparameters, and we knew that that would not be as big of an issue for a human gait. So this gave us a lot of confidence. It told us that this approach can identify individual specific slip-like dynamics that describe center of mass control. And I should note that in this synthetic data set, we did use asymmetric dynamics, and it was able to identify those. So let's take a look at what happens in unimpaired locomotion. To do this, we took a subset of the data from my prior study, 12 unimpaired adults walking in bilateral passive exoskeletons. We also had them walk in shoes only. And we collected data in one individual with post-stroke hemiparesis, walking in the same conditions. We reduced the data collection time by 1 minute per condition, just to avoid fatigue. The conditions we extracted were the shoe, the zero stiffness, and our highest stiffness conditions. And what we expected, specifically for the shoe condition, was that the structure of the template signatures, these subject-specific descriptions of center of mass control, would be consistent across unimpaired adults and provide essentially an archetypal structure. We also expected that with the addition of exoskeleton stiffness, the limb stiffness in the template signatures would increase. So that's a change in parameter. Finally, for our individual with post-stroke hemiparesis, we expected that signatures would reflect their impairment, and we didn't know what would happen with ankle exoskeletons, so that was a more exploratory case study. So let's first look at the shoe-only walking condition. Just to remind you, these are our template mechanisms: stiffness and resting length, damping, and rotary stiffnesses and damping in the frontal and sagittal plane. What you're looking at here are 4 hybrid regimes: double limb support, single limb support, and swing. We've got our mechanisms on the bottom, and the vertical axis represents the percentage of participants for whom each template signature term or mechanism was selected. So what you can see is that in both double and single limb support, slip-like dynamics describe center of mass accelerations, being the stiffness and resting length. That was in over 96% of participants. We also found that a subset of participants, there's center of mass control was described by rotary mechanisms, generally stiffness in the frontal and sagittal planes, but also a little bit of damping. And we didn't identify swing dynamics, which isn't surprising because the swing leg won't generate external loads on the center of mass. So what that told us was fairly interesting and confidence inspiring. The first is that we can identify an archetypal slip-like template signature for unimpaired gait, though there are individual specific terms that may describe differences in center of mass control during double limb support. Our findings are actually consistent with literature, where spring legs are far more common than rotary mechanisms when modeling gait using templates. And that's exciting because we identified these mechanisms purely from data without prior assumptions about model structure. So what happens when we change, when we perturb gait with an ankle exoskeleton? Well, we made 2 comparisons. The first is between the shoe and the 0 stiffness condition. That told us what the impact of the exoskeleton frame and mass were. The second comparison was between 0 stiffness and high stiffness, which told us what the effect of a stiff exoskeleton would be. We found, just to orient you quickly, we've got, again, our mechanisms on the bottom. The vertical axis is our coefficient magnitudes. We isolated leg stiffness here just for scale, so you could see everything. And what we found, the hatch marks denote the different exoskeleton conditions. What we found was that we didn't identify changes in limb stiffness in any of the conditions. There was some variability between participants, but that suggested that center of mass control is insensitive to passive ankle exoskeletons. What that suggests, because the exoskeleton should impact center of mass control in some way, biological control may be modulated to maintain an overall nearly invariant task level controller. But what happens following neurological injury when an individual's physiology and motor control may be altered? To address this, we looked at the same experimental condition in one individual with post-stroke hemiparesis. Looked in the same conditions. For the sake of time, I'll tell you one punchline here, which is that the template signatures were able to identify differences in the paretic and non-paretic limbs when walking in shoes only. identified that the paretic limb was generally stiffer and that the limbs contributed differently to first and second double limb support. When we look specifically at the ankle exoskeletons, we see a couple interesting things. Just to remind you, we make two comparisons to understand the impact of the frame and then the stiffness, and our three conditions you can see up here. We found first that there was an effect actually of the exoskeleton frame on limb stiffness and single limb support, which is really interesting. And we think that's because this individual's paretic ankle inverted quite a bit. And it may be that the exoskeleton frame restricted that inversion, enabling a slightly stiffer limb. We also observed a small effect of exoskeleton stiffness on rotary mechanisms and second double limb support, which corresponds to terminal stance, suggesting that the spring in the ankle exoskeleton may have stored and returned energy in a way that assisted forward propulsion during terminal stance. So that tells us that task level control may be more sensitive to ankle exoskeletons following neurological injury. That was one individual, it's a case study, so I think it represents an interesting area of future research to see how those structures differ between individuals. But this gave us a lot of insight, and the main contribution, I think, of this work was to improve our ability to quantify task level responses to ankle exoskeletons. By introducing a physics-informed data-driven modeling framework, we were able to select subject-specific walking signatures that were consistent with literature. And we did that purely from data, which is exciting because it suggests that we may be able to rapidly run a large number of hypothesis tests about mechanisms automatically using this type of approach. We also showed that passive exoskeletons were insensitive to, or did not alter task level control in unimpaired adults, but that may change following neurological injury. To summarize the culmination of my dissertation research, I used physiological models to study ankle exoskeleton impacts on gait in children with cerebral palsy. That contributed to exoskeleton simulations to an existing open source data set of children with cerebral palsy and crouch gait. I then used phase varying models to predict kinematic and myoelectric responses to exoskeletons, showing that a linear phase varying model is a good representation of unimpaired kinematic responses, but that we need to learn a little bit more about those responses to predict muscle activity. This also created an open source code base and data set of long time series of walking with ankle exoskeletons. We had 12 subjects with 4 minutes over per condition for 4 exoskeleton conditions. So it's a large data set that I think can help researchers test different dynamical data-driven models of locomotion. And finally, I used a physics-informed data-driven modeling framework and introduced that to the biomechanics community to quantify task-level controlled walking, showing that it seems to be insensitive to exoskeletons in unimpaired adults, but that may change following neurological injury. If anybody's wondering, why should I care at this point? Here's a bingo chart for you. I'm not going to read everything, but just to summarize where I think the big impacts can be of this research. From a clinical perspective, this could inform predictions of a particular device's efficacy for an individual with a motor impairment. And it could also be used to explain differences in walking function, either with or without ankle exoskeletons. For engineers and designers, these tools can be used to predict responses to exoskeletons for real-time control or offline device design. And for the scientific community, the tools and knowledge that I tried to develop here really provide a foundation for the investigation into mechanisms driving locomotion using these data-driven techniques. And I should note that the tools that we developed really should generalize across assistive devices such as prostheses or interventions such as biofeedback. So I think there's a really exciting future for this type of research. In particular, I'm really excited about the potential to integrate data-driven modeling with experimental design. The two are often, especially as I came into biomechanics, they seem like very distinct entities. But today we have these really powerful real-time experimental techniques, such as human-in-the-loop device optimization, real-time biofeedback, treadmill training, that could be combined with data-driven modeling techniques to rapidly probe different mechanisms about locomotion to exoskeletons or other interventions. And I think that's a really exciting area of research going forward. Also, stemming directly from my latest research, being able to understand task level control following neurological injury, I think paints or could have big impacts for rehabilitation and assistive device design. Understanding how interventions alter task level variables in walking function may be very powerful in improving device efficacy. And finally, especially in this last year, I've started thinking more about the notion of optimality of an exoskeleton. And in reality, if anyone has ever seen a child, you know that they don't move at a single speed. They don't always walk, they run, fall over, roll around. Even adults don't always walk at a single speed. And so I think understanding how optimal an exoskeleton is in the broad context of locomotion, not just in the context of steady state walking in a lab, is really important and could, advancing that research area and our knowledge could really help design devices across a range of individuals and motor function levels. With that, I hope I didn't talk too fast. Up next for me, I will be stepping away from exoskeletons for a little bit. I have set up a postdoc at Emory University with Drs. Lena Ting, Tricia Kazar, and Gordon Berman. It's a super exciting team to work with. I'll be studying responses to gait rehabilitation paradigms in individuals post-stroke. So I'm really excited to dive into a bit more neuromechanics and rehabilitation and head back to the Southeast. So with that, I would like to thank my fearless advisor, Dr. Kat Steele, for her eternal patience. She put up with me longer than anybody else out here, and I'm incredibly grateful for that and for all the guidance that she provided. I'll thank my committee again for their feedback, and again, I look forward to their questions. Of course, my collaborators. Speaking of people who put up with me, going, I think, in order of how long they dealt with me, I first want to thank my family and my partner Katie for just being supportive as I've gone through my PhD. I'm very grateful for that. I have a lot of people at the University of Washington to thank. From my lab, from the people who welcomed me in, and I've gotten to see them move on in all sorts of directions, to the people who are there now. I'm really thankful for the lab environment they've helped create and what they've taught me along the way. The many undergrads that I've had the privilege of working with. It was great to have somebody help you pursue those questions you don't quite have enough time to dig into, and it's been really neat to see them develop and move on. And I look forward to them being far more successful than I could ever dream. And finally, I really should thank a large number of faculty and staff members, and really everybody here who have given me opportunities to grow as a researcher and a mentor and a teacher. I and I should say, who have made this experience, for the most part, very, very enjoyable. Because a PhD is all about fun. So with that, I will stop talking and I'll be happy to take questions while you enjoy some of my failures. This is my version of how sausage is made on the way to the publications. So thank you.
Thank you, Michael. We will now turn it over to questions from the audience. We'll have the committee save their questions for the closed Zoom session. But if anyone else has questions, feel free to either raise your hand, unmute, or type it in the chat.
I'll let you guys moderate. I can't see everybody. So if somebody has a hand raised, I will.
Any brave takers? Or are you just going to turn them over to the committee to begin?
Heather's got a hand raised.
Oh, thanks. Go ahead, Heather. I just saw your puns.
Fun with a PH, of course. Thank you, Michael. This was an awesome presentation. So you talked a little bit about this at the end in kind of when you did your bingo grid. And so my question is more kind of in that clinical space. And you specifically mentioned this idea of assistive device efficacy, whether that's an AFO or exoskeleton or whatever that technology might look like. And so I'm wondering, do you have a future vision? Is there an ideal of what that would look like, incorporating the type of work that you did, both computationally as well as with the device that itself? Do you envision it being kind of like a trial environment or a test drive strategy kind of a thing where people are able to try out different settings with this technology to then help with device prescription? Like, what, I'm curious to hear your thoughts on that.
That's a great question. And I'll go back to that slide so everybody can see it. I can see a number of ways of that being implemented. I think this comes in very much in what I talked about with the integration of experimental and computational methods. One option would be to use something like a musculoskeletal model as an initial guess. And that's been done when designing controllers for powered ankle exoskeletons, I think in the last couple of years, where you generate a simulation, you say, okay, I think this design will be most useful for this individual. We know this model is going to be wildly wrong for an individual with a motor impairment. So let's use that as an initial guess and tune from there. I think a really interesting approach is closer to something like human-in-the-loop optimization, where you have a robotic system that is attached to an exoskeleton device, sort of an emulator, and that device can rapidly change the properties of the exoskeleton. So you can emulate a passive device or a powered device, and using that in conjunction with some model-based framework, if you want to test certain outcomes that can be hard to measure experimentally, or if you want to build a representation of the individual, you could have them undergo different, essentially exoskeleton perturbations or walk with different types of designs, and then try to build that representation and predict what would be best for them.
Thank you.
Great. Any other questions? Ava, Julia, any questions?
Michael, this is Ben. I got a question for you.
Oh dear, let's hear it.
So as you're talking about this emulation type of stuff, have you thought about this in terms of either identifying like really ideal properties or maybe finding the best in show of what's available in the market? Do you have any thoughts as to where you might like to direct that kind of idea?
That's a good question, and I'm going to start with a safe answer, which is that is not my decision. that should be the decision of a practitioner, right? Somebody who's really working with the individual and knows the constraints of the space. Ideally, the tools that we've developed and some of the knowledge can generalize across different device designs or different even devices. So particularly, the reason I like parameterizing response as a function of torque was because torque is something that generalizes across devices. And then once you find that, you can play with the parameters to try to elicit that desired input or constraint. So yeah, I think it's really up to the clinician. Yeah, that's tough. I want to say, yes, we should be making custom devices for everybody, but I'm not sure we're quite at that reality yet.
Thanks and congratulations, Ben.
Thank you.
Hey, Michael, I try to save you for at least like a minute from your committee. Great presentation. So a lot of what you highlighted, and so, you know, there's heterogeneity in CP, there's heterogeneity in responses. I hadn't realized this before, but I think every study you showed, either yours or previous research, had a different outcome measure that they were examining that they were saying is heterogeneous. So do you think your like third research aim, these slip models, is center of mass something that all studies should be examining? And have you looked into or thought about using metrics from these slip models like leg stiffness, and if it could be predictive of knee flexion or some sort of kinematics, and using that for predictive for children with CP or unimpaired individuals currently?
Yeah, it's an interesting notion. Yeah, depending on the study, they'll look at different outcomes. The notion of center of mass control and using that as essentially an additional constraint to predict certain joint or muscle level responses is certainly feasible. The notion of template models originated in that they provide a foundation upon which to add that physiological detail and add knees and ankles. So I think that is a super interesting direction to go, to say, okay, suppose we constrain an individual to walk with the same control across all of these conditions. How, if we put that, like you said, into, say, one of your predictive simulations, give Jerry a center of mass controller, we might expect to see across different individuals, different joint kinematics emerge from that. And as a result, different muscle activity. So it's a really nice hierarchy that I don't want to say every study should look into, but I think especially when you're studying pathological gait, you need to build from the ground up, because these nice physiological models were developed for unimpaired adults, right? Those might not generalize to kids. Those might not generalize to individuals with motor impairments. So we tune them typically after the fact, but building from the ground up for a specific individual may provide a little bit more resolution into where different responses to exoskeletons diverge or emerge. So yeah, I think that's definitely a reasonable way forward.
Awesome, thank you.
Can I ask one question?
Juan. Yeah, I saw Juan on mute. So we'll do one more question from Juan, and then we'll turn it over to the committee.
All right. Well, it was a very nice presentation, and congratulations in advance. So I'm wondering whether have you thought about considering the strategies of prescribing AFO from the clinicians, because clinicians has a lot of experience and they know how to predict the outcomes when they just evaluate, you know, barefoot walking with their participants. So maybe that could be gives insight to build up any like a prediction algorithms and so on. So I'd like to hear, I'd like to listen your thoughts and opinion about this.
How many clinicians are on here? Be very careful with what I say. That's a great question. You're essentially talking about reverse engineering the clinician and using, trying to use some of their considerations to inform design or modeling. And that is a really interesting approach. Clinicians have a lot of experience. They may or may not express what they consider when they look at somebody walk and think, oh, that person will respond in a certain way to a certain device. But there are a couple of challenges there. If we look in the case of Gillette's data, where they looked at children with cerebral palsy, they were walking with their prescribed AFOs. And there were highly variable changes in kinematics, some in a direction that would be contrary to the AFO prescription. So while, yes, I do think clinicians are often able to predict those responses, the data suggests that something may be missing. So I think it would be really interesting to go in and try to extract from clinicians what they use to encode gait. I think actually, maybe back in 2016, 2017, Keisha was working on a similar study where they tried to understand what clinicians looked at to quantify motor control. And if I remember correctly, it was pretty hard. It was hard to extract those meaningful bits of information. But I think that's a super, super interesting research direction where you collect a bunch of data, you interview clinicians to try to extract what they think predicts responses to an exoskeleton. And then you see if you can build a dynamical model that's consistent with the clinician's perspective. Yeah, I think that's a really interesting idea.
All right, thank you.
Great, well, thank you everyone for joining today. Please join me in giving Michael one more round of virtual applause. And then we will ask everyone except for the committee to jump off the Zoom call, and otherwise, committee stick around, and then we will continue our closed Zoom session. So goodbye, everyone.